Hi folks, Chris McClure. Welcome back from the weekend. I was out of town for the past 3 days. Back with you this week. Hopefully you are um, looking to finish your midterm exam. I know some of you have already got them sent in. I'll be grading a group of those later this week. But today we are going to start Chapter 6. Chapter 6 is about the famous normal probability distribution. Actually, it's a whole family of distributions. We're going to take a look at the standard normal today. Now, what exactly is a normal distribution? Well, a normal distribution is one in which we have a continuous random variable, not discrete like the binomial and the Poisson distributions. Rather, the normal distribution is continuous in that a continuous random variable is one that can take on any fractional or decimal value along the spectrum. So think heights and widths and lengths. For example, normal distributions, when you look at the graphs, they are bell-shaped. If you've ever heard of the bell curve, well, we're talking about the normal distribution. Normal distribution is going to be characterized by the mean, which is mu, and the standard deviation, which is sigma. And here's the scary-looking algebraic function which determines the probability density function for the normal distribution. You don't really necessarily have to know this, but we do have tables and technology that will allow us to evaluate normal probabilities without having to evaluate the scary function. Okay, so we move on to section 6.2, in which we'll be talking about the standard normal distribution. Now, like I said, there is a whole family of distributions that are normal, characterized by some mean and standard deviation, but there's only one standard normal. And the standard normal is the one that has the mean of 0 and the standard deviation of 1. The attractive part about the standard normal is that you can look up probabilities in a table. Why would you want to do that? Well, you can convert any other normal distribution to the standard normal by subtracting the mean and dividing by the standard deviation. So we're going to look at some key ideas here in calculating normal probabilities here for the standard normal, by taking a look at z-scores and finding areas under the curve to the left and to the right of z-scores that correspond to probabilities, and vice versa. Or looking at areas under the curve between two different z-scores and interpreting that probability. Excuse me. There are many different continuous distributions out there, some as simple as the uniform distribution. A continuous random variable has a uniform distribution if its values are spread evenly over the range of probabilities. And if you were to look at the graph of a uniform distribution, it would look like a rectangle. But we're more interested in the standard normal distribution, which is going to be more bell-shaped. But here's kind of an example of uniform distribution. And don't worry, I'll go back to the previous slides here in a minute, but I want to show you the rectangular shape. We're talking about voltage level for a battery that is spread evenly between 123.0 volts and 125.0 volts. All right. And like I said, there's an even probability over that interval of length 2. 125.0 minus 123.0 is 2. 2 times 0.5 is 1. This is a probability density curve, and one of the things that you need to know about probability density curves is that the entire probability, meaning the area under the curve, must be exactly equal to 1. And if you were to take a look at the area of this orange rectangle, this area of the orange rectangle is exactly equal to 1. Let's go to the previous slides here. A density curve is the graph of a continuous probability distribution, and it must satisfy these two probabilities. Number one, that the total area under the curve must be equal to 1. Why? Because for any probability distribution, the the sum of the probabilities for the entire sample space must be equal to 1. That corresponds to the area being under the curve being equal to 1. Because on the horizontal, you have the random variable values. And the interval or range of values for that random variable makes up the sample space. Every point on the probability density curve must have a vertical height that is either 0 or greater. Doesn't make sense for it to dip into negative territory. There is a correspondence between area and probability for density curves. And going back to this uniform density function regarding voltages for batteries, notice that on the horizontal axis you have a range of values for the random variable x. In this case, x, the random variable, corresponds to selected voltage levels. If we want to calculate the probability of a particular value for the random variable, that's going to always be equal to 0. The only way that we could have non-zero probabilities for a continuous random variable is that the random variable needs to be over some interval. So it makes sense for us to talk about the probability that your voltage is between 124.5 and 125.0, for example. All we need to do is look at the area that's under the curve between x equals 124.5 and 125.0. And what is this area? Well, you can just use simple geometric argument that says, well, the height is 0.5, the width is 0.5, 0.5 times 0.5 is 0.25. So there's a 0.25 probability. In other words, a 1/4 probability that if you were to randomly sample a battery, that it has a probability of, it has a voltage of between 124.5 and 125. Or in other words, there's a probability that it has a voltage greater than 124.5. Another way of saying it is that 1/4 of the batteries have voltages greater than 124.5. Here's what the standard normal distribution looks like. It's that prototypical bell curve with the peak corresponding to a mean, median, and mode of 0. We don't typically talk about the mode and median for continuous distribution, but for continuous distributions that are symmetric, it's going to happen that the mean, median, and mode for that distribution always lines up under the peak. But as we shall see in a later lecture, that when you have skewed non-symmetric distributions, that the mean, median, and mode do not line up under the peak, and that the mean is dragged out toward the tail of the skewed distribution, for example. No need to worry about that. We're only concerned about the normal distribution for chapter 6. It's nice and symmetric, mean of 0 under the peak, and then you go out to the left and to the right by so many standard deviations. Going to the right of 0 on the horizontal axis, you have 1 standard deviation, 2 standard deviations, 3 standard deviations, and so forth. To the left of 0, we have -1, -2, -3, dot, dot, dot. 1 standard deviation corresponds to a z-score of 1. Number of standard deviations from the mean assigned quantity corresponds to a z-score. Okay? How do you find areas under the curve? So you can calculate the probability that z takes on some range of values over some interval. Well, to calculate these probabilities, we can use a table, or we can use technology. And we strongly suggest that you learn to use technology. I will show you a couple of examples on the TI-84, but I'll also show you the table. Now, we don't use StatDisk, Minitab, or Excel in this class. We just use tables. I'm sure that you can find out how to use it in StatCrunch. I've never used it on StatCrunch because using the TI-84 calculator is pretty easy, which I'll show you how to do. And it just basically involves finding your normal CDF command on the TI-84 calculator. Here's what the table looks like. You'll find this toward the end of your textbook. You'll have a couple of pages. Sometimes they call this the z-table. Going down the lower left, you'll look up your z-score. That takes you out to the 10th position. And then to get out to the 100th position, or 2 decimal place, or your 2nd decimal place, you'll just go across the column headers. So if you want to look up, say, -2.49, here's -2.4, and go out to this column. And you see there's a 0.0064 that's associated with the z-score of -2.49. Or this 0.0495 is associated with the z-score of -1.65. -1.65. Now, what do those decimals mean? Let me go back here. What do these mean? These are probabilities. These are area under the curve to the left and from the left. To the left of the z-score out to -infinity. This is only for the standard normal distribution. You can convert any other normal distribution into a standard distribution, into a standard normal distribution. And remember, the standard normal distribution has a mean of 0 and a standard deviation of 1. And like I told you, it has 2 pages. The first page usually has the negative z-scores, and the second page has the positive z-scores. And like I have already said, those decimal numbers right here in the main body of the table, and this is just an extract of that table, by the way, but these numbers here in the middle, these are probabilities. These are areas under the curve to the left. I'll show you a picture here in a minute. Now, when working with the graph, avoid confusion between z-scores and areas. They are related, but here's how they differ. Z-score is the distance along a horizontal scale for the standard normal distribution. It's the number of standard deviations from the mean. But the area is the area under the curve between the given 2 z-scores, or to the left of that 1 z-score. Okay? So let's take a look at an example so we can get a good feeling for how to look up probability for the standard normal distribution. We're going to take a look at the bone mineral density test that can be helpful in identifying the presence of osteoporosis. The result of this test is commonly referred to as a z-score. This is a normal distribution with a mean of 0 and a standard deviation of 1. Suppose that we randomly select one adult who undergoes a bone density test. Find the probability that the result is a reading less than 1.27. Again, less than 1.27. So to the left of 1.27. Now here's a picture of the standard normal distribution. Here we have a z-score of 1.27. Notice it's to the right of 0. It's going to be between z equals 1 and z equals 2. Now, when we want to calculate the probability that a z-score is less than 1.27, this is what the mathematical notation looks like. Z being less than 1.27 is an event. And we're going to calculate the probability of this event. So, what is this area under the curve? Well, of course, you can see it's 0.8980. How did we get that? Well, here's kind of an extract from that table. Again, table A-2. Look down the lower left, or the left-hand column, go down to 1.2. And then go over to the 0.07 column, so you'll have 1.27 for the z-score, and then get the probability of 0.8980. And that tells us that the probability of a random adult having a bone density less than 1.27 is 0.8980, as in 89.80% of adults have a bone density of less than 1.27. That's how we can interpret that probability. 89.8% of adults have bone densities less than 1.27. Now we're going to take a look at this next example. Using the same bone density test, find the probability that a randomly selected person has a result above negative 1.00, which is then considered to be in the normal range of bone density. Now, again, looking at the standard normal distribution, the mean of 0, standard deviation of 1, well, someone who's got negative 1.00 bone density score is going to be right here. It's one standard deviation below the mean. Now, what we want to find is the probability that someone has a bone density, bone density above negative 1.0. Now, the probabilities given to us in the table are for areas to the left of the z-score. So what we'll do is we'll look up the z-score of negative 1.00, find the area, meaning the probability, that's to the left of negative 1.00. It'll turn out to be 0.1587. So where does that come from? Well, I need to show you the z-table. Let me see if I can pull up the z-table. Just to give me a second here. I'm going to go into my computer here, see if I can find a z-table. I'm pretty sure I have one. I'm a pack rat when it comes to saving old documents here. Let's see. Do I have one right here? Actually, I think it's in my finite math. Give me just a moment here. Here's my z-table. This is from a different textbook, but it's essentially the same thing. Now, here's the first table, the first page of a z-table. And I'm going to go down here to negative 1.0, and this first column is the 0.00 column, right? You see it? So negative 1.00. And notice that it has a probability of 0.1587. Okay? There we go. So we saw that the area to the left of negative 1.00 is 0.1587, and I just showed you how to look that up. That means that the area to the right is 1 minus 0.1587. Remember, the whole area under the curve is 1. Because the whole area under the curve is 1, then 1 minus 0.1587 is 0.8413, meaning the probability of getting someone with a bone density score of greater than -1 is going to be 0.8413, meaning 84.13% of people have a bone density score of greater than -1. Now, what I want to show you now is how to use your calculator. I'm pulling out my calculator here. I'm going to clear the home screen, go into the distribution menu. You have to hit second and then this button here, and then go down to normal CDF, not PDF, but CDF. CDF means cumulative distribution function, and hit enter. Now we want to put in two numbers right now. We want to put in a left endpoint and a right endpoint. Now if we want to go from negative infinity, well, we don't have an infinity button for the calculator here. But how we can indicate negative infinity is by inputting a large number, like 1 times 10 to the, or -1 times 10 to the 99th power. So this right here is what serves as negative infinity. So as x varies from negative infinity to, say, -1, area under the curve, and we'll do a close parentheses, hit enter, and we got 1.586, almost 1.587. And then if we want to do 1 minus that answer, there you go. So you get 0.8413. So that's how you could calculate that probability. Or if you want to go from -1 to positive infinity, that will still give you the same thing. So normal CDF, which is option 2, from -1 comma to infinity. So we'll go 1 times 10 to the 99th power and you get the same answer as before. So this tells you the area under the curve from x equals -1 to x equals 1 times 10 to the 99th power. X, z, same thing for this distribution. X, z, they're random variables. So sometimes I'll refer to x. That just means the generic random variable of discussion. Now, we could also talk about finding the area under the curve between two z-scores. Like, what's the area under the curve between -1 and -2.5? That's the same thing as saying, what's the probability that if we randomly select an adult, that he or she has a bone density score of between -1.00 and -2.50? Now, if we're going to use a table, then what we need to do is find the area to the left of -1.00, which we already have, and the area to the left of -2.50. And then subtract the big area minus the small area, the big area minus the small area, in order to get the area under the curve between the two z-scores. Now, we have already found that the area to the left of z, according to the table, is 0.1587. The area to the left of z equals -2.5 is 0.0062, again, according to the table. And then if you were to subtract these two, 0.1587 minus 0.0062. So again, this big area of 0.1587 minus area of 0.0062, then you end up with 0.1525. So the probability that if you were to randomly select an adult, give them a bone density test, the probability that they have a z-score between negative 1.00 and negative 2.50 is 0.1525, at least using the scores from the table. Let's see how we do it on the calculator. Pull up my calculator again. There's my calculator. All right, we want to go to normal CDF under the distribution menu, normal CDF, left endpoint, negative 2.50, comma, and the right endpoint is negative 1.00. And hit enter. And you get 0.1524. Don't worry about the fact that out to the 10,000th position that your answer is going to vary from what you got from the tables. 1.524, or 0.1525. The MyStatLab should not be counting it wrong if you use the calculator or the table. It does have some forgiveness, so to speak, if your answer is off by 1/10,000th or 2/10,000th. Okay. Anyway, moving along. So make sure that you know how to use your calculator and the table, how to calculate probabilities. Okay. Now, a little bit of notation. When we say that z, or whatever random variable that you're using, typically we use z for the standard normal, that z lies on some interval, that's an event, and we calculate probabilities of an event. So if we want to calculate the probability that z lies on some interval from a to b, this is what the notation looks like. Otherwise, if we want to calculate the probability that z is greater than some number a or less than some number a, this is what it looks like. I know that it's a little bit disorienting to have mathematics use numbers mixed with letters, but we need to talk about general purpose sort of topics without involving a bunch of numbers. So our letters of the alphabet stand for numbers. So finding z-scores from known areas is the so-called working backwards sort of problems. If you know an area or probability, then for under the curve, then you can look up the corresponding z-score. So you can sketch a bell-shaped curve, identify the region under the curve that corresponds to the given probability. If that region is not a cumulative region from the left, work instead with a known region that is a cumulative region from the left. Because when you look up those areas in the table and work backwards to find the z-scores, remember, those probabilities are for areas under the curve to the left. So you locate area to the left and then work backwards to find the corresponding z-score. Okay? So for example, if we wanted to find the z-score corresponding to the 95th percentile or 0.95 area under the curve to the left, what do? Well, we can pull out a table. So here's my table. And I'm going to go on to the second page here of the Z table, look in the body of it, and find the probability closest to 0.95. And notice it's going to be right around here, about halfway in between these two probabilities. So look at the z-score to the left is 1.6, and then you could either go with 0.04 or 0.05. If it were me, I would say 1.645 to cut it right down the middle. Okay. So 1.645 is that corresponding z-score. And because of the fact that the area is greater than 0.5 or 50%, we should expect that z is going to be positive. Remember, when the z is to the left of 0, it's going to be negative. That corresponds to an area under the curve from the left that is less than 50%. Let's take a look at this example. Using the same bone density test that we've been talking about already, find the bone density scores that separate the bottom 2.5% and also the top 2.5%. Now, let's take a look at this right here. Area under the curve to the left is 0.025. So what we want to do is find the z-score corresponding to the area under the curve to the left of 0.025. Now you can see here it's negative 1.96, but I'll show you on the table how to get that. So let me pull out my z-table here. So area under the curve corresponding, of 0.025. 0.025, what is the z-score corresponding to the area under the curve for area 0.025 to the left? So I'm looking here in the table, there's 0.027, 217, 222, 228, 233, 239, 244, 250, right here. Now here's the probability that's closest to our area to the under the curve to the left. And then look to your left here, you got negative 1.9 and 6, right? So the z-score is negative 1.96. And likewise, if you want to find this z-score right here, where you have an area to the right of 0.025, well, if there's an area of 0.025 to the right, that means 1 minus 0.025, which is 0.975, go down here, here's 0.975 right here, and look at the corresponding z-score to the left is 1.96. Which should not be surprising because the normal distribution has a symmetric quality to it. So if there's area of 0.025 to the left with a z-score of negative 1.96, that means that the z-score of positive 1.96 corresponds to an area to the right of 0.025. So once you find the z-score corresponding to the bottom 2.5%, then take the positive of that number to get to the z-score for the top 2.5%. So, to answer the question, the bone density scores that separates the bottom 2.5%, and same thing for the top 2.5%, that's going to be negative 1.96 for the z-score that separates the bottom 2.5%, and 1.96 is the bone density score for the top 2.5%, meaning 2.5% of the population have a bone density score of greater than 1.96, and 2.5% of the population have a bone density score less than negative 1.96. And the middle 95% of the population has a bone density score between negative 1.96 and positive 1.96. What you needed to know for this example is to, if you were given a probability corresponding to an area or vice versa, area corresponding to a probability under the curve, how to find the corresponding z-scores. and then how to interpret those. Let's take a look at an example here. For the standard normal distribution, a critical value is a z-score separating unlikely values from those that are likely to occur. We will see this in the future when it comes time for us to do hypothesis testing. So when you see z sub alpha with that subscript alpha, that denotes the z-score within an area of alpha to the right. So let's take a look at an example. Find the value of z sub 0.025. In fact, we've already seen that. That was actually 1.96. 1.96. We didn't even need to do anything. Now, let me show you before I sign off here how to look up z-scores according to areas to the left on the calculator TI-84. I'm going to go into the distribution menu and select option 3, which is inverse norm. So if I want to find the z-score corresponding to, 0.975 area to the left, and you'll notice that it comes back to be approximately 1.96. When you use this command of inverse norm, it's going to ask the calculator to compute the z-score corresponding to 0.975 area to the left under the curve to the left of the z-score. So you tell it the area to the left and it'll come up with the z-score. Okay, folks, with that, we are done for today, and we'll continue with section 6.3 tomorrow. Have a good day.